Uh, Hello once again everyone and welcome to steady state analysis in STAAD.Pro. So our session will consist of 3 parts, and let's go and start with theoretical background, uh, overview of the steady state analysis in STAAD. So the response of the systems to harmonic excitation is classical topic, classical problem in structural dynamics. And the steady state analysis, it can be applied to evaluate, for example, response of structures that are subjected to unbalanced rotary equipment or motors, and as well as earthquake loads, sudden excitations, and also some other types of harmonic loads that can be used in engineering problems. And you know that the total response consists of 2 parts. So the transient part and steady state part. And as we see on this graph, the solid line represents the total response and the steady state response is a dashed line. And the difference between them is transient response, which will decay with time at some rate if the damping is applied. So the harmonically applied forces response will remain. So this is why it's called the steady state. So the excitations will continue at some rate and according to some formula. Okay, so it's some law depending on the display damping and the model characteristics. So so this is the plot of harmonic loading function, and probably you have seen that in our manual, STAAD.Pro manual for the time history analysis. So they are quite close analysis types, but different. Okay, since the time history analysis deals more with the transient part of the excitation and the steady state deals with the steady part of that graph. Okay, and when the periodic force is applied to structure, so it will reach some steady state after going through some transient behavior. So we will look into this part of the graph, and the steady state response can be computed without calculating the transient time history response prior to steady state condition. Okay, so to model the structure to capture the dynamic response, so we need to have the stiffness of the structure, so the structure itself. We need to have the active mass distributed, so, and we need material characteristics. So having those components, we can go ahead and continue with the steady state analysis. So this is the same principles as we use for any other dynamic analysis. So the masses should be defined. So first step to define the masses. After we have modeled the structure and applied the material characteristics, so we apply the masses and we tell the program how they are distributed. Okay, so we are providing the loading information to the program, and the program will convert the loads to the masses. So we need to think about all of the directions where our structure will be excited. So all of the possible directions, so probably in real life models, so that should be all 3 directions. Okay, and it is a good recommendation to have those load values unsigned, so either all positive or it's better to have all of them positive, so they will not be interfering or mutually excluding one mass from another during the different modes of vibrations. And the distributed weights will be lumped to the neighboring load. So when you're applying the loads, they will be lumped at the nodes. So you need to think of the number of nodes, number of divisions along the, let's say, beam, so that the dynamic response of that member will be correctly captured. Okay. So there is a note that the node should be created at the location of concentrated weight to ensure that the mass is lumped at that exact location. And also you need to think about the flexibility of the structure. So applying too many nodes may make your structure way too flexible. Okay, so think of the, let's say, finite element meshing, etc. before you apply the loads. And the mass modeling is recommended to be performed by using the reference loads in STAAD, so the type of loads that will not be analyzed by their own, but they will be referred when they're called out in the load cases. Okay, so you can specify the load type as mass, and the mass will be calculated. Okay, and the program will report the masses in all three directions, and it can be given to an engineer in the text file. Okay, so if file called input file name dash, so your file name underscore mass txt, so it will have the masses. Okay. All right, the next characteristic which is necessary for steady-state analysis is damping. So there are several ways, so three types of damping can be applied. So damp, so this is a single damping ratio for all of the modes. Okay, so it is a user input. The next one is mdamp, so this is the individual damping ratios for individual modes. Okay, so the program will calculate according to the command given. And the cdamp, the third option, where the program will calculate the damping based on the damping ratio of material and springs assigned. And this is a program calculation. Okay, so let's go and review the workflow and controlling parameters for steady-state analysis in STAAD.Pro. So there are four basic scenarios that are available in STAAD.Pro for steady state. So there are four cases. So case one, where a single force and frequency at applied as joint force loads. Second case is when a single force and frequency applied as ground motion. The next case is where several force and frequencies applied as joint force loads. And fourth scenario, when several force and frequencies applied as ground motion. And you can notice that where the single forcing function is applied, force and frequency applied, it is called steady. And when there are several frequencies, it's called harmonic in the command. So you can see that corresponding command on the right side showing begin steady force, begin steady ground, and begin harmonic force and harmonic ground. So these are the differences between steady and harmonic notations. And as Badruddin noticed, the perform steady-state analysis command execution depends on STAAD.Pro Advanced license. So you need to have the advanced license. Okay, and before you specify that perform steady-state analysis command, you must have a load case which contains a model calculation command. Okay, so this load case will define the weights and moments of inertias for agent solutions for steady state and harmonic analysis. So before we have specified masses, next we need to extract the modes and frequencies, then specify and perform steady state analysis command. Okay, and you can probably, for those who have already used steady state, they know that steady state analysis cannot be specified from graphical user interface, and all the steady state analysis commands must be entered in the STAAD editor or input file. Okay, so these are four basic scenarios, inputs, as we described before. Okay, and you can see that after the perform steady state analysis command, so we have the inputs which is starting with begin steady, and at the end of that we have end command. So that begin and end, everything what is between those commands are the steady state analysis data, so which contains the list of additional frequencies, steady state load cases with joint loads or ground accelerations or phasing, phase angles entered there. Okay. All right, so let's start with the steady force loading type. So the first scenario, and here is the basic input, and again on the right side we see the extract from the STAAD editor file. All right, so steady force command. So we can provide the frequency, so steady state frequency in cycles per second. Okay, and below the joint loads that will oscillate. Okay, so the damping ratios can be specified. Okay, so the default value is 0.05, so which is 5% damping. If you leave 0 or you don't enter the damping, so it will be reverted to the default 0.05. Okay. So next one, so the joint load. So we have to specify the joint load. So we will see how that looks in the input file in the example models a little bit later. So we need to apply the joint load, so that will be the load that is oscillating, so not representing the dynamically active masses as we mentioned before during the mass calculation, but the oscillating masses. Okay, so it can be in all three, so that joint load can be in all three directions, and if necessary, so the square parentheses, so in brackets it's showing the optional input, so it not necessarily needs to be entered, but if the phases, so phase angle or phase log is different in some directions, so you can go ahead and specify that as phase X, Y, Z directions and provide that phase angle. Okay. So additionally, you can specify the copy load command. Okay, so you can place it to use the equivalent joint loads from prior cases. Okay, so that will enable using some complex loading commands like self-weight, floor load, wind load, etc. Okay, and you can have multiple lines for that input, so that is an optional. Next, Let's see the steady ground motion loading. So steady ground frequency, so the steady state frequency in cycles per second should be entered. Very similar input as in previous steady force input. Okay, so you specify the damping ratio. Okay, so and it can be so absolute, relative, so the ground motion results in output file will be relative to the ground unless the absolute is specified. Okay, so the graphical results will show you the relative. Okay, and the ground motion in all possible three directions, and the acceleration, so which is ground acceleration as multiple of g. Okay, so acceleration due to gravity. All right, and the displacement can be specified, which is ground displacement in current units of length, and the phase angle in degrees. So if it's not specified, so that will be taken as 0, so which means there is no phase shift or phase lag. Okay, so let's move to the harmonic scenarios where several frequencies are specified, and to tell the program that there are multiple frequencies, so you can go ahead and specify the frequency command. So this is an optional command, but if so this is the way how to tell the program what kind of frequencies are to be used. Okay, so FLO, so this is the lowest frequency, F high, which is the highest frequency to apply, and the NTPS parameter, so number of plot frequencies to include between the natural frequencies calculated. So the default value, so if you'll not specify that NTPS, so that will be defaulted to 5. Okay, so in brackets there is an explanation: 7 if fewer than 10 modes used, and 3 if more than 50 modes are used. So that is a intermediate points of results for frequencies. Okay. Next, so we have modal, so optional cases, optional causes, optional command which calls to extract natural frequencies between those highest and lowest frequencies entered by the engineer. Okay, and they will be added to the list of foreseen frequencies. All right, and flist command, so which will list a number of frequencies that will be added to the harmonic analysis. So I would say the frequencies of interest of an engineer. So at some specific frequency, the result will be calculated and given result in the output and in the post-processing. Okay. So with scenario of harmonic force loading is given here. So we need to tell the program that it is harmonic force. So again, there is similar input as before. So we provide the damping, we provide the joint load information, and optionally we tell the program if there is a phase shift or phase lag. So we tell the program in which direction it goes. Okay. And an optional command, amplitude, can be used. Okay. So if, let's say, so we can provide the, so in help manual there is a little bit more information about that. So there is a two options to enter the amplitude. So you can specify the it by the parameters A, B, and C, and the program will calculate the amplitude according to those values, or you can just tell the program amplitude command, as we see here below, so amplitude, and provide the amplitude versus frequency versus amplitude pairs. Okay, so I would say at which frequency which amplitude will be used, and that A1, as we see, A1, A2, AN, so those values will be multiplying the joint load applied. So let's say if 100% of joint load is applied at this given frequency, so we will give that A1, let's say 1 unity, and that will be multiplying our joint load. Okay. All right. Next one is harmonic ground motion loading. All right, so we tell the program that it is a harmonic load, and we provide the damping ratios for, let's say if it's damp, so that will be damping ratio for all modes. Okay. So we tell the program that it is a ground motion. Okay, so you can enter one ground motion command for each global direction in one input. Okay, you provide the direction, you provide the acceleration, which is ground acceleration as multiple of acceleration due to gravity. Okay, so all right, displacement, which is ground displacement in current units of length, and the phase angle in degrees, so it's an optional parameter again. If it will not be specified, it will be taken as 0, so no phase shifting. Okay. Next, the amplitude versus frequency specification, which is an optional input. Okay. So it will be used when the ground motion acceleration is a function of frequency. And if you will not enter that amplitude data, so for some given direction, so then the acceleration will be same as acceleration F3 in the ground motion command for that direction. Okay. Or you can specify the amplitude just by giving the command amplitude and providing again frequency amplitude pairs. Okay. And you can have one ground motion and amplitude command for each global direction. And finally, we get the harmonic steady state results. So you can request the harmonic displacements to be printed, and for some given, let's say, joints or all joints, by default it will be given to all of joints, but not of them may be points of interest in some specific problem. So you can go ahead and specify the list of joints to give the results. So there is, we see the relative joint displacement screenshot from the output file. So all of the degrees or directions reported. Okay. And the program gives you the modal responses, phase angles for each of 6 directions of motion, displacements for 6 directions of motion, velocities and accelerations. Okay. So we can also notice that the results for a steady state response are absolute maximum of displacements. Okay, very similar as to any other dynamic analysis in STAAD.Pro. So as well as forces, stresses, so the corresponding harmonic response, which is consisting of series of, say, steady state responses for a list of frequencies, will be calculated. Okay, and so the results will be positive. Okay, and so if, let's say, you need to perform the code checking, so the beam zero parameter should be used. Okay, so probably in this case you will go and add the steady state response to the dead and live loads for, let's say, one combination case, and extract the steady state response from those loads for another combination cases. Okay. All right. Okay, so let's probably go and see how the steady state analysis looks like in STAAD.Pro. All right. Okay, I will share my screen. Okay, so this is a truss model, and it is already having the section properties assigned. So we have assigned the steel material everywhere, and support conditions are provided. So let's go to the loading. So we have specified the reference load case with self-weight in X and Y directions, and we have the Fy force, which is 3,000 pounds, applied to the nodes. Okay, so we have node 8 and node 6. So these nodes are, so the masses will be lumped at these nodes. So we have two motors that will, let's say, lift some weight, and those motors will induce the harmonic load on the structure, and we need to go ahead and check how that is affecting our structure. Okay, so this is why we have specified those masses. So the motors, so these are the loads in reference load command. So we have the loads that will represent the dynamically active mass. The next step, so we have created the load case. So with the model calculations requested command. So since we have specified the reference load case in the definitions, so there is no strict requirement to go and duplicate that mass calculation in the load 1, but it's not a mistake, it's okay to specify. So alternatively, if you are not used to reference loads, you could have specified the dynamically active mass in that first load case with model calculation requested command, so alternatively. Okay, and that's it. So we have specified all the information in STAAD.Pro graphical user interface for steady state analysis, and next step, we must go to the editor file. Okay. And here we see, so this is our input, so we have specified the reference load. We have requested for the modes and frequencies to be extracted, modal calculation request command. Next, we have entered the perform steady state analysis. Okay. So all of the steady state analysis scenarios, so steady force, harmonic force, steady ground motion, harmonic ground motion, so they have the similar structure. So they begin with perform steady state analysis and then begin and some scenario command and end. Okay, so you can practically find those scenario examples in help manual, and you can copy and paste those commands from the help manual, paste it in the editor file, and you will have a pattern of correct sequence of commands for that scenario, and you can go ahead and alter the parameters. So that is quite okay to do. So, and let's review what we have here specified. So begin harmonic force. So that will be harmonic force scenario where several amplitude frequencies are applied to our structure. And here is our frequency specifications. So the highest and lowest frequencies. So everything will begin with the frequency 0 and end with frequency 50 cycles per second. So that would correspond, let's say, 3,000 revolutions per minute. Let's say some electric motor is pulling the weight, and so the NTPS 5 is specified, but actually if I would leave that unspecified as 5, so the default is 5, so it will be used, depending also on the number of modes. Next, modal command, so the modal natural frequencies will be added to the frequency calculations, and the list of frequencies of my interest. So I want additionally to calculate the response of the structure, so the steady state response at frequency 1, 5, 25, and 40. Next input is harmonic force damping. So I've specified it as 0.03, which is quite okay for steel structures. Next command is joint load, and I have a phase shift in y direction 30 degrees. Okay. And the joints 6 and 8 will receive the force Fx 300, and let's check on the units. So that will be inches and pounds, so 300 pounds of force, and in y direction again 300 pounds of force. And here is the command amplitude in y direction. Okay, so the amplitude is 1, okay, at frequency. So this is frequency versus amplitude. Okay, so we have okay, maybe there is, so it is probably frequency versus amplitude, and I think it is a little bit vice versa. It's amplitude versus frequency right now I've entered. Maybe let me check. Okay, just give me a second. Should be frequency. The first number should be frequency. Just let me check my notes. Okay. Okay. All right. So okay. So it it should be amplitude versus frequency. So amplitude versus frequency. So right now this input reads as amplitude is 1, frequency 1. Okay, it's correct. So the next one, so every frequency will have the same amplitude. So the load lifting amplitude is the same at each frequency here. Okay, and the command print harmonic displacement list for those two nodes are of interest, and the command end. And once again, I would like to get back to the amplitude. So everywhere I have 1, okay? So this amplitude as a multiplier will be applied to the joint load. So if we have here 300 fx, 300 fy, so this means at each amplitude that load will be amplified by 1. Okay, so the same 300 at each amplitude will be used. Okay, if let's say at some point of at some frequency the load is decreasing or increasing, so we will correspondingly apply the parameter. Okay, so let's go and review the results. So we did not do any change to input file, and the model was already analyzed. So let's first jump into the output file. Okay, so we have the eigen solution. So some notes about the masses from the load case 1. It's okay. So we find that the 6 modes of default command for 6 modes, so we did not enter the cutoff mode shape command, so maybe some more modes would be required, for example, but it's okay. We will have those for 6 node modes. Okay, so I can see that in Y direction, so maybe some more additional modes of vibration to be added to reach the better mass participation. Yeah. Okay. Next, if we go to harmonic, so we see here so different calculations, so frequency, so we see additional at frequency 0.476, so 4, so this means 4.76. Okay, at amplitude 1. Okay, and we have all 6 modes giving the natural frequencies. Okay, and the damped frequencies. All right, participation factors for each mode. All right, and the list of output frequencies. So 1, 5, 9, 13, etc., etc. 25 we requested. Okay, 45, and a little bit more, frequency 53. All right. Okay, 40, sorry, 40. All right, and we see that the lower limit is frequency 4.76 hertz or cycles per second, and the upper limit was 50. Okay, so this is so those pairs go like this. Okay, and exciting frequency number 1, 4.76 hertz, and we have our results, so displacements, phase angles in degrees given. Okay, and the joints. So in Y direction, so we have in current units, so inches and pounds. Okay, so it's something 0.8 thousandths of an inch, something like that, maybe a little 8 over 10,000. In Y direction, and the relative velocity is given, acceleration is also given in terms of g, acceleration due to gravity. Okay, and the next frequency, 5 Hz, the results for that frequency given, and etc. Okay, for each and every frequency we have the results printed in the output file. Let's go to the post-processing. Okay, so if we go to the, let's say, node displacement summary, so we find that all the displacements are positive. So these are the results, so the maximum results from all of the modes, all right? And if we go to layouts, so we can review the mode shapes from the drop-down, so 6 modes. We can see the frequency as with any other modal calculation performed, so those results are given. And additionally, we have the steady state, displacements, velocity and acceleration graphs. So if we go and select a point, so point of interest right now is joint 6, so we have the results for displacement versus frequency, and here we have that peak frequency given, so at 9.53 Hz we have the displacement, and displacement is given here in millimeters. Okay, so probably this is the setting of my probably this is my setting here. So if I see section structure units, so you see displacement is in millimeters, so to be consistent with input I will say it's inches. Okay, so displacement in inches, so 0.02 inch at that 9.539 frequency. Okay, so we have those intermediate result points, so not only where we requested 5, 40, etc. So we have up to 50. Okay, so that's the displacement in x direction. And if I'll go and check the displacements in y direction, so this is displacement y, so we see that with increasing the frequency, okay, so our displacements go lower. Okay, and we can go and check, let's say, node number 8 or any other node of the structure if we are interested in any other node. So we can go ahead and click on the node and get the corresponding graph. All right, and if we go to results, layouts, and velocity, so we can again review the velocity versus frequency graphs and acceleration. Okay, acceleration is meters per second square. All right, so the acceleration in y direction, x direction. Okay, so we don't have results for the z direction since we have not specified inputs in that direction. Okay, so let's go and review another example model which is very similar but with a different approach. So there is a portal frame where we have specified the masses in terms of self-weight in all 3 possible directions and the force in units, so kilograms and meters, so that would be 3,000 kilograms in each direction, so that will represent our lump mass. and we requested the model calculation uh, extraction of modes and frequencies. And let's go and jump into the editor file. So we have specified here uh, again the steady state analysis command, perform steady state analysis. Again, this is the harmonic force, very similar input of frequency and number of frequencies of interest, okay? But we have specified the different amplitudes in different directions, okay? So we have applied the joint 5 is the middle node, joint 5. And here, again, I've imagined that there is a motor or some lifting mechanism which is uh, imbalanced, so it has some imbalanced masses inside the mechanism, and when it starts rotating or starts operating, so that disbalanced force is higher, and with the increasing speed of the motor, so that is the oscillations, vibrations due to imbalanced mass is going down. So let's say a manufacturer provided us with that information. So normally they provide the graph of force at different speeds of the motor, okay, in balance force. So I have applied the force Fx 0.15, Fy 0.30, and let's check the units. So units, meters, and kilograms. So I have applied that specifically. So that's actually not the entire force acting, but this is some fraction of that load, and I will multiply that by the amplitude. So frequency versus amplitude given in the amplitude X and amplitude Y inputs, okay? So here at amplitude, at frequency 0.1 cycles per second, so we have multiplier 100, so that would be effectively 15 and 30 kilograms, so 100% of that imbalanced force will be applied to the structure, okay, that will oscillate. Next, it is increasing, so decreasing, so with increasing frequency, the imbalanced force is decreasing, and finally getting to the highest operating speed of the motor, 25 cycles per second. So we have 1. So 1 multiplied by 0.15 and 0.30 in both directions, okay? So which will be 0.15 kilograms and 0.3 kilograms in X and Y. So we could have different values for that, but just for representation purpose, I just copied that for the Y direction also. It can also have amplitude can be different in Z direction. So just for example, I have used that in this way. And I have requested to print the harmonic displacement for joint number 5. Okay. And the analysis was performed, and we can just go into the output file, and I'll go to harmonic displacement at, let's say, first frequency. So we see that the relative joint displacement in Y direction is as follows. So that is in meters, unit meters, okay? And at different frequencies, so we can see that, let's say, first frequency, exciting frequency is 0.1, so that the first frequency. And next we have different frequencies, and let's see the last one, so which is 25 hertz, and I can check the displacement, so they're way lower than first one, definitely. And we can go ahead and review in the post-processing. So I'll go to layout and displacement versus frequency. So I'll select my node number 5, and if I'm looking at the displacement in y direction, so I can see that there is a peak displacement value, so it's in millimeters, so 0.4 millimeter at the frequency of 6.985. Okay, so this is the most dangerous frequency for that structure under this motor operation. Okay, and we see that with increasing frequency we have drastically dropping the displacement value. Okay, and if I'll just go to displacements and summary, I'll see, so we have that maximum vertical displacement 0.41 in y direction reported and 0.66, which again is maximum value. So I'll try to find at which frequency it happens. Okay, so let's go to displacement. So I see that 0.66 millimeters is in the x direction is achieved at 3.807 hertz. Okay, so at different speeds of that motor, the maximum displacements in both directions are happening at different revolutions of that motor. Okay, so we have reviewed that. So additionally, as I mentioned before, so the beam results are also available. Okay, so beam results are available, but they are I would say should be used in conjunction with other load cases. So it's better to have two, let's say, combination cases where that force is extracted from our load cases and another combination where it is added, as in many cases with dynamic analysis results. Okay, so this is quite a simple review of steady-state analysis. One scenario we have reviewed, but it gives the idea how it works in STAAD.Pro.